y is 2x cubed minus 3x squared minus 1. So straightforward to differentiate this. We multiply the power by the number in front. 3 by 2 is 6. Take 1 from the power, so x cubed becomes x squared. Multiply the power by minus 3, so 2 by minus 3 is minus 6. Take 1 from 2 to get 1. The derivative of a constant is 0. Now we can do the next question by multiplying out this expression here and gathering up all the terms, and then we can differentiate term by term, or we can apply the product rule. So I'll do it both ways. Okay, so I'm going to multiply this out. We can do that because neither of these brackets are raised to a power. If one of them was raised to a power, we would have to raise the thing to the power first before we multiply. Anyway, 2x squared by x cubed is 2x to the power of 5. 2x squared by minus x is minus 2x to the power of 3. 2x squared by 2 is 4x squared. 3x by x cubed is 3x to the 4. Then we have minus 3x squared. Then we have 6x. For next term, plus 1 into this gives us x cubed minus x plus 2. Okay, gathering up the terms, we have one x to the 5 term. We have one quartic term, x to the 4. We have two of these. Put these together to give minus 1x cubed. 4x squared minus 3x squared is actually plus 1x squared. Should be a plus. 6x minus 1x gives us 5x, and then finally we have the plus 2. So that's, let's call this thing y. So the derivative can be written dy dx. Of course, we could call this thing f of x. In that case, the derivative would be called f dash of x or f prime of x. So differentiating each term, the first term give us 5 2s are 10, x to the 4. Next term, 4 3s are 12, x to the 3. Then we have minus 3x squared. Then we have 2x. Then we have 5. The derivative of 2 is 0. Now I'll repeat this question using the product rule. So we'll call the first expression u and the second expression v. So u is 2x squared plus 3x plus 1. V is x cubed minus x plus 2. We need the derivatives of both of these expressions. So we need du dx. So we're differentiating u with respect to x, or we could write u prime of x if we like. If we're calling, if we're calling this thing here u of x. Okay. So du dx here would be 4x plus 3. dv dx is 3x squared minus 1. Alright, so here's the product rule. Okay, dy dx is the first function times the derivative of the second function plus the second function times the derivative of the first function. So that's the way I remember it. First by derivative of second plus second by derivative of first. So here's the first function, u, times the derivative of the second function. So we multiply these together, u by dv dx, and we add on to it v times du dx. Okay, now if we expand out all this and simplify, we should get this thing here. Okay, 2x squared by 3x squared is 6x to the 4. 2x squared by minus 1 is minus 2x squared. 3x by 3x squared is 9x to the power of 3. 3x by minus 1 is minus 3x. Then we have plus 1 by 3x squared minus 1. Well, that's just 3x squared minus 1. Next we have x cubed into 4x plus 3. That's 4x to the power of 4 plus 3x cubed. Then we have minus x into 4x plus 3. That's minus 4x squared minus 3x. Then we have plus 2 into 4x plus 3. That's 8x plus 6. Okay, let's look at the x to the 4 terms. 6x to the 4 plus 4x to the 4 is 10x to the power of 4. Next, let's look at x cubed terms. We have 9x cubed plus 3x cubed, that's 12x cubed. X squared terms, we have minus 2x squared plus 3x squared, that's plus 1x squared. We have minus 2x actually we have a minus 4x squared that I nearly forgot. So we plus 1x squared minus 4x squared, that's minus 3x squared. Okay, so we minus 3x squared, that includes this term here. Now let's look at the x terms. We minus 3x minus 3x is minus 6x, plus 8x is plus 2x. Then we have the constant term, plus 6 minus 1, that's plus 5. Okay, so it's a bit of a mess, but anyway, we get the same result as before. It's probably easier just to multiply these two expressions together and differentiate term by term than to use the product rule. But in other situations we will have to use the product rule. Say for example one of these expressions is raised to a power. Let's suppose that the second expression is raised to the power of 10. Now we certainly won't be raising this to the power of 10 and multiplying the result by whatever u is. We'll have to use the product rule in a situation like that. But it's straightforward to multiply these out, gather up the terms and differentiate term by term. So y is 3x divided by 2x plus 5, and we want the derivative. Now one way to do this is to use the quotient rule. So we have a quotient of expressions here. That just means a ratio of expressions. The one on top is called u and the one underneath is called v. Now if we just had a single term underneath, we would not have to use the quotient rule, you know. We could just break it down quite easily, but you see we have two terms in the denominator. When we have two terms we have to use the quotient rule. Actually there is another way of doing it which I'll get to, but I'll start by using the quotient rule. So we note down what u and v are and we take the derivatives. The derivative of 3x is 3. The derivative of v with respect to x is 2. So the quotient rule says that if y is equal to u over v, then dy dx is v times du dx minus u times dv dx, all divided by v squared. So we have to multiply v by du dx. That's 3 times 2x plus 5. Well, that's going to give us 6x plus 15. Then we have a minus sign. So I put a bracket after this, because we'll be multiplying by minus 1 of course. We have to multiply u, which is 3x, by dv dx, which is 2. So 3x by 2 is 6x. Well, we've only one term here, minus 6x in brackets. Well, I can ignore the brackets there. It's minus plus 6x, which is minus 6x. And the whole lot is divided by v squared. V is 2x plus 5, and we have to square it. Okay, these cancel out, so we could just get 15 over 2x plus 5 squared. And we want the value of the derivative at x equals 0. So we can write this in the following way. This vertical line means at x equals 0 is 15 divided by 2 times 0 plus 5. Well, that's just 5 squared. So we have 15 divided by 25. That's 3 over 5. So 3/5 will be the slope of the curve, of this curve here, at x equals 0. Okay, so that's the geometrical interpretation that I discussed before. 3/5 is how quickly the function is changing at x equals 0. By the way, we are given this information here, which is not actually relevant to answering the question, but I'll just briefly mention what it means. 2x plus 5, the denominator, cannot equal 0, because we cannot have division by 0. Okay, so x can take on values such that 2x plus 5 is not 0. So for example, x cannot equal, so that means that x cannot equal minus 5 over 2. Okay, if we rearrange this, we get it. If 2x plus 5 is 0, then x is minus 5 over 2. So x cannot equal this particular value. That's all that this thing says, because if x does equal minus 5 over 2, then we have division by 0, and that's not defined. Okay, I'll go through this question again, but I will rewrite this thing. Well, we have 2x plus 5 in the denominator, so we can write this as 3x multiplied by 1 over 2x plus 5. So I can write this quotient as a product. Now, 2x plus 5 by itself means 2x plus 5 to the power of 1, of course. Anything by itself means it's raised to the power of 1. But you see, we have 1 on top. We've 1 over something raised to a power. So we can take that something, namely 2x plus 5, and raise it to the negative power. So the power is 1, so we negate it to get minus 1. So you see, we have a product of functions. So we can use the product rule. So we can call the first function u and the second function v. So we write down u and v. We get the derivatives of each of these. Now, we have something raised to a power, and we certainly won't be expanding this out. So we leave it as it is. We use the chain rule. We treat what's inside the bracket as a single term. So we take the minus 1 in front of the bracket and subtract 1 from minus 1. Now minus 1 is minus 2. So that's the first step in the chain rule. Treat this thing as a single term. Say x to the power minus 1 would give us minus 1x to the power minus 2. Okay. The second step in the chain rule is to differentiate 2x plus 5. The derivative of 2x is 2. The derivative of 5 is 0. So we have 2 times the minus 1. That gives us minus 2 times this thing here. Now you don't multiply into this, of course. This is raised to the power minus 2, so you don't touch what's inside here. But since 2x plus 5 is raised to the power of minus 2, we can write it as 1 over 2x plus 5 to the power of plus 2. Okay, that's the meaning of a negative power. And of course we can then multiply minus 2 by the 1 to give minus 2. Alright, next we apply the product rule. So dy dx is one of the functions, say u, times the derivative of the second function. Well, that's this thing over here. Plus the other function v times the derivative of the first function. Now I'll write 2x plus 5 to the power minus 1 as 1 over 2x plus 5 to the power of plus 1, or just 1 over 2x plus 5. And that's multiplied by 3. Well, if it's multiplied by 3, multiply 3 by the 1 on top to give it 3. And we get a common denominator of 2x plus 5 squared. Okay, both denominators go into this. Like just simplifying here, 3x by minus 2 will give us minus 6x. 2x plus 5 squared into 2x plus 5 squared goes once. 1 times minus 6x is minus 6x. 2x plus 5 into 2x plus 5 squared goes 2x plus 5 times. 2x plus 5 by 3, well, I can write it down like this, 3 times 2x plus 5. Well, you can see that that's going to give you 6x plus 15. So just like before, we get our answer of 15 over 2x plus 5 squared. The diagram opposite shows graphs of the quadratic function f of x equals x squared plus 3x minus 1 and the line L1. Okay, so the line L1 passes through the point 2, 0. So here is the point 2, 0. Alright, so the graph is a parabola. It's an upright parabola because we have a quadratic function, okay, and the x squared term is positive, so that's why it's an upright parabola, U shape. Alright, so we want to find the slope of L1 using a slope formula. Well, we can clearly see 2 points on this line. It's very clear that one of the points is 2, 0 and the other point is 0, minus 2. Okay, this point is on the y-axis, so the x value is 0. So we could note down those 2 points. I'll also construct a right angle triangle here as well. But first of all, I'll just note down the 2 points and apply the formula. So one of the points is labelled x1, y1, it doesn't matter which one of course, and the other point is labelled x2, y2. So we have -2 minus 0 on top, and we have 0 minus 2 underneath. So we have -2 over -2, which is 1. So our line has a slope of 1. And if we construct a right angle triangle here, we can also see that. We get the vertical distance between the points. We just basically count the squares. The vertical distance between them is 2. And the horizontal distance between the 2 points is 2. So the slope is rise over run, 2 over 2, which is 1. And we make this positive because the line is sloping in this direction. So I put in the plus sign to emphasize that. The line has a positive slope. If the line was going the other way, we would have to stick in a minus sign after measuring vertical and horizontal distances. Okay, so now we want to get f prime of x, which is the derivative of this thing here. Well, that's easy to see. I'll just write it down again. X squared plus 3x minus 1. So the derivative, written f prime of x, is 2x plus 3. Now we know from previous videos that the derivative of a function is the slope of the curve. It's the slope of the curve at a general point x. Okay, you know, it's the slope of the tangent to the curve at the point x, but the slope of the tangent to the curve is the same as the slope of the curve. If we zoom in on a tiny section of the curve, the slope of the curve is approximated by the tangent. Okay, so as we zoom in closer and closer to the point of contact of the tangent to the curve, we see that the slope, the curve and tangent become indistinguishable. Okay, if we really zoom in, okay, curve and tangent are essentially the same. So the slope of the curve at the point is the same as the slope of the tangent to the curve. So we've seen that before. So f prime of x is the slope of the curve at a general point x, but we want the slope at a particular point. We actually want it at x equals -1, which is actually this point here. Okay, the point of contact is at x equals -1. How do we write all of this here? Well, we want the derivative at -1. Well, we can just write f prime of -1. We plug -1 into our formula that gives us the slope of the curve at any point, any value x. So we get -2 plus 3, which is 1. So the slope of the curve at x equals -1 is 1. Alright, so that's the slope of this tangent. Okay, so we got it two ways, using 2 points on the tangent, the point and the slope formula, or by using differentiation. The line L2 is perpendicular to L1 and is also a tangent to the curve f of x. So let's just try to roughly indicate that. So we have a line that's perpendicular to L1, so it'll slope like this. It'll have a negative slope. Okay, sloping this way. But it's also tangent to the curve. So it's somewhere, must be somewhere around here. So this is the line L2. Okay, it's perpendicular to L1. By the way, it looks like it's tangential at this point here, and we can almost read off the coordinates. The x value is -2, the y value is -3, but we'll get to that. Okay. The question is to find the coordinates of this point. We can't just read them off from the diagram. We have to, how would we work this out? It mightn't be as clear cut as it is here, or reasonably clear cut. Well, we have the slope of this tangent line because we have the slope of L1. See, L1 is perpendicular to L2. So the slope of L1 is 1, which we've seen. So the slope of L2 is got by inverting the slope of L1 and changing the sign. If we invert the number 1, we get 1. Change the sign to get -1. Okay, so That's the relationship between the slopes of perpendicular lines. Or if we multiply the slopes of perpendicular lines together, we always get minus 1. So we explained that in previous videos. So we just take the slope of L1, turn it upside down and change the sign. So we get minus 1. And you can see we should get a line with a negative slope. Alright, if we rotate this line through 90 degrees, we haven't actually changed the shape of this triangle. It's still going to be 2 over 2, but it's going to be in the negative direction, so it's going to be minus 1. Right. But now we apply the fact that the slope of a tangent to a curve at a particular point is the same as the slope of the curve at this point. So let's suppose that the x value of this point is x. Okay, pretend that we don't know. It's actually minus 2, but pretend that we don't know that it's minus 2. So slope of this line is the derivative of the function at x at a general point x. But let's suppose it's this particular value x. Okay, and we know what this is. This is 2x plus 3, but we know that this must equal minus 1 now, because we now know that the slope of this line is minus 1. So we have to solve this equation here. So we are working backwards. We know the slope of the tangent to the curve at some point x. So the coordinates of this point are going to be x comma f of x. Okay, given by the equation of the curve f of x. The y value is given by f of x, which is the quadratic function involving x squared. So we know the slope of the tangent. We don't know what x is, so we have to work backwards. Okay, we have to work back to find out what x is. So solving this equation gives us 2x equals minus 4 and x equals minus 2, just like we see in the picture. We can see from the picture that it looks like x is minus 2, and indeed it is. So we found the x value of this point. Now we go and get the y value. So we have to sub 2 into the function. So we're talking about a point on the curve, and the curve is given by this quadratic function here, so we have to get f of 2. So here is f of x, and from this we get f of 2. So 2 squared plus 3 times 2 minus 1, so we get 4 plus 6 is 10. Sorry, it's minus 2 squared, of course. It's f of minus 2, not f of 2. It's minus 2. Right, so we get 4 minus 6 minus 1. So that's minus 2 minus 1, which is minus 3. And if we go up here, we can see that it certainly looks like the y value of this point is minus 3. Given that f of x is 12 minus x squared, find the value of x for which f prime of x is 0. Alright, so let's get the derivative. The derivative of 12 is 0, the derivative of minus x is minus 1, the derivative of minus x squared is minus 2x. That's the derivative, and we set it equal to 0. Okay, we want to set it equal to 0. So we need to solve this for x. So we have minus 2x equals 1, x equals minus a half. Okay, so at x equals minus a half, the slope of the curve is 0. So this thing here is slope of curve. Okay, if you draw a rough sketch of this curve, actually, get something like this. As a matter of fact, it'll cross at 12. That's the constant term. When x is 0, y is 12, or f of 0 is 12. It's an inverted parabola because the x squared term is negative. Okay, minus 1x squared. Okay, so we get it's a quadratic, so it's a parabola. As a matter of fact, it doesn't quite look like that because at x equals minus a half, the derivative is 0. So this is actually more like what it will look like. crosses at 12. Well, we don't have to worry too much about this, but this is something that we will need to know for other questions, finding the turning points and so on. So at -1/2, the slope of the curve is 0. So the tangent to the curve is a horizontal line. So this is where the maximum point on the curve is. It's at x equals -1/2. Okay, next we have a cubic function. Okay, the highest power is 3. We want the coordinates of the local maximum and local minimum point. Now, all cubic functions look like this. They have 2 turning points. One is called a local max, because in this locality this point is the highest point of the curve, and this point is called a local minimum, because in this locality this point is the lowest point of the curve, but actually there are points that are below this point, but just in this locality we have a minimum. Okay, so it could look like this, or it could look like this. Sometimes a cubic doesn't have any turning points, but anyway, this one must have turning points. Okay, just to get back to this, we can see that at a max the slope of the curve is 0. The curve is neither increasing nor decreasing. For values of x less than, let's say it looks like this, for values of x less than this value, the curve is increasing. For values of x just greater than it, the curve is decreasing. So at this point the curve is neither increasing nor decreasing. The tangent is horizontal, which means that its slope is 0. But the slope of the tangent is the same as the slope of the curve at the point of contact, which is going to be 0. Okay, and the slope of the curve is the derivative of the curve. So slope of curve is the derivative of this function, which we can write as g prime of x. So if we work that out, x cubed becomes 3x squared, the next term becomes -18x, and the next term becomes +24. The last term is 0. So we want the slope of the curve to equal 0. So we want to put this equal to 0. Okay, and then we have to work backwards to find out what this value of x is, for which the slope of the curve is 0, for which the tangent is a horizontal line. We will find that there are actually 2 values of x, of course, because there are 2 turning points. So when we solve this equation we get 2 values. That makes sense. We have a quadratic equation, so it has at most 2 solutions. Okay, so let's go and solve this. We could divide all this by 3, or we could leave it as it is and just use the formula, plug in for a, b and c, but I'll try and factorize this. X squared minus 6x plus 8 equals 0 divided by 3, which is 0. Okay, we get the factors. I put -4 here and -2 here. -4 by -2 is +8, and if we gather up these terms we get -2x minus 4x is -6x. So the product of these 2 factors is 0, so that means that either of them must be 0 to give 0, you know. So if x minus 4 is 0, we get x equals 4, and if x minus 2 is 0, we get x equals 2. So at these 2 values we have turning points. So actually the curve doesn't so much look like that. We have turning points at x equals 2 and at x equals 4. Now we could have a local min at x equals 2, and we could have a local max at x equals 4, so the curve could look like that. Or it could be the other way around, of course. We could have a local max at 2 and a local min at 4. So to decide what the curve looks like, we have to get the full coordinates of the points. So we just have the x coordinates of the turning points. So to get the full coordinates, to get the y values that go with these 2 values, we need to use the fact that the points are on this curve. So they have to satisfy this. So we get g of each of these numbers. So we get g of 2. So that's going to be 2 cubed minus 9 times 2 squared plus 24 times 2 minus 20. and we get g of 4. So 2 cubed is 8, and we have minus 9 by 4. 4 9 36 plus 48 minus 20. That's 0. And as for the other, 4 cubed is 64 minus 9 times 16 plus 24 by 4 minus 20. That's minus 4. So one of the turning points is 2, 0. That's this one here. 2, comma 0. So when x is 2, y is 0. And the other turning point is 4, comma minus 4. So that's going to be somewhere down here. Okay, so we can see that because there are only 2 turning points, this one must be a local max. And this one here must be a local min. Okay, so the curve must look something like this. A stone is thrown vertically upwards. The height s meters of the stone after t seconds is given by this formula here. We want to get the height of the stone after 1 second. Alright, so s is the distance or height. So we want the height. This is the height as a function of time. We could write it like this, s of t. But we want the height after 1 second, so we could plug 1 in here and work this out. 5 times 4 times 1 minus 1 squared. Just plug 1 in for t. So we get 5 times 4 minus 1 in here, which is 3. So that's 15. So the height is in meters, so it's 15 meters. Show that the stone momentarily stops 2 seconds after being thrown, and we want to find its height at that time. So if it momentarily stops, its speed is 0, but its speed is 0 at 2 seconds, at t equals 2. So that's what we want to show. So how do we get the speed? Well, speed is the derivative of this thing here. Now it's s is a function of t, so the derivative will be written ds dt. And this should remind you of the formula for the average speed of an object. It's the distance travelled. So s stands for distance now, and it doesn't stand for speed. So s is a distance. Well, actually ds is a infinitesimally small distance, and dt is an infinitesimally small interval of time over which the distance ds is traversed. This is the time. So you see, this is a reminder of the formula for average speed, distance travelled over time taken, where in this case the time taken is vanishingly small. Okay, we're getting instantaneous speed here when we get the derivative. That's the speed at an instant. So that's what you do. You differentiate to get the speed. So you have to differentiate this function using the usual rules for differentiation. We can write this thing in a better way. 5 is just a constant out in front, so we can just multiply the 5 in. Well, it doesn't matter what 5 is. It could be, if it was 5t, we just multiply 5t into this. But anyway, we get 20t minus 5t squared. Okay, and if we differentiate this, well, 20t becomes 20. Minus 5t squared becomes minus 10t. Right, so it's a straightforward derivative. So this is the speed at any time. Now we're interested in the speed at 2 seconds. Now we often use the letter v for speed. So v is a function of time given by this formula. So we want the speed at 2 seconds. So we could write it like this. We could write this as t to emphasize v is a function of time. So the speed at 2 seconds should be 0. Okay, because we're given that the stone stops at 2 seconds. Speed is 0. So if we plug 2 in here, well, you see we get 20 minus 20, which is 0. Okay, that's what we had to show. So the speed would be in meters per second. Okay, the distance is in meters. ds stands for vanishingly small distance traversed by the stone, and dt is the vanishingly small interval of time that it took the stone to traverse that distance ds. So ds is in meters, but time is in seconds, so it's meters over seconds, meters per second. Next we want to show that the acceleration of the stone is constant. Well, speed is given by 20 minus 10t. Now the acceleration is the change in the speed divided by the time taken for that change to occur. It's analogous to the speed of an object. It's the distance over time. Here we have not distance but change in speed over time taken for that change to occur. And we're dealing with instantaneous acceleration here. Okay, so the time interval is vanishingly small. It approaches zero but actually does not equal zero because we cannot divide by zero. It's a quantity that approaches zero when we take the limit. Anyway, we just differentiate this quantity to get the acceleration, so that's straightforward. You just differentiate this formula for the speed to get the acceleration. Differentiating 20 gives us 0, differentiating minus 10t gives minus 10. We just get a number. We get something that does not involve time. Okay, the acceleration is minus 10 no matter what the time is. So the rate of change of the speed is constant. It's always minus 10. So it means that the speed is decreasing by minus 10 meters per second each second. This would be written as minus 10 meters per second squared. So this means that speed decreases by 10 meters per second each second. How do we know that the speed decreases? It's the minus sign tells us that actually. If you wanted to look at a graph of the speed, it would look like this. It would be a straight line. See, it's a linear function of time. Okay, at 0 the speed is actually 20. T is 0, we just get 20. And the speed decreases uniformly by 10 meters per second each second. So after 1 second, the speed will be, well, it's meant to be 10 actually, isn't it? Because decreases by 10 meters per second each second. So okay, the 1 should be here, more like. Scales are different on both of these axes, but that doesn't matter too much. So t equals 0, the speed is 20. At t equals 1, the speed is 10. Okay, that's what an acceleration of minus 10 means. After each second, the speed is decreased by 10, and after another second, 2 seconds, the speed is going to be 0. 10 minus 10 is 0. Of course, we could imagine finer and finer intervals. We could imagine what happens after half a second. The speed is going to decrease by 5. Okay, and we're dealing with continuous decrease or uniform deceleration. Well, I should just say uniform deceleration, not continuous deceleration. Just uniform means constant deceleration. The minus sign means that we have a decelerating stone.